Hello, hello, hello. Good afternoon, good evening, good morning. Yeah, welcome to day three of the lesson Foundation to Machine Learning. Today we're going to talk about logistic regression and classification metrics. What is classification? We all understand what classification means. Classification is putting things into categories or buckets. As we are very much aware in our community, we have classes. We have high class, we have low class. Even the cars that we drive, we have high class, car that we drive. So I'm very sure this is not going to be a problem to understand what classification is. So I don't have to dive deep into that. But previously we predicted numbers of sales using total sales, the column total sales. So today we're going to predict category in terms of classes, like I said. So instead of predicting a number, now we just want to predict a class. Um, the first one we're going to talk about is binary classification, which means there are exactly two classes that we have in our data set. Uh, One of the best scenario that we have in the industry is the one that classifies if an email is a spam or not spam. Another one is for commercial industries. They want to see if your maybe what you are spending on your advertisement is it's bringing about high sales or low sales. So that's a classification problem. Another one we could be familiar with is fraud. In the fraud industry, fraud department of an industry, we usually classify if a transaction is fraudulent or not fraudulent. So all of these examples are classification problem. Uh, Take for example, if you're hacked that given a transaction features, maybe you are in an industry and you're one of the data analysts there, and you're given this question, you're given a transaction features, they want to know if a transaction is going to be a high value or low value from a particular customer. So in that case, the first thing that comes to your mind is like, this is going to be a classification problem. So as soon as you know that, you know what to do, you know where to go, you know which model to use. Uh, so our question today, let's say we have a transactions feature and we like to classify it to high value and low value. But based on our current data set, you remember we do not have high value or low value on our columns. So the first thing we do is you engineer your feature. I know we talked about feature engineering, how we produce another feature based on an existing feature, or let's say we produce columns based on our existing columns. So here we're going to talk about how do we extract I says column and I says features from our existing features. So the best way to go about it is using our median, because median does not really put um, consideration into consideration the outliers in the data set. Medians really do not get affected with our outliers, so we suggest or we highly recommend you use median in this kind of in this type of problem. If you have a very normal distributed data set, so you can use mean. But for this type of data set that we have some outliers, high values, extremely high values, you use median to categorize high sales and low sales. So we say if the total sales is above the median value, you consider it a high sales, which is one. And if it's below the median, then we say high sales is zero. So the new column name will be high sales. The feature that we are engineering, we call it high sales. So this is called engineering a target. A target. So we create that label because we want to predict that particular label from our existing data set. Um, so the industry standard for regression for for classification problem is logistic regression. This is a bit different from linear regression, which is normally used for our linear regression problem or predicting the numeric values. For this type of problem, for classification problem, we use logistic regression. Although the name looks the same with linear regression, but when you hear logistic regression, just know this is a classification algorithm and it's not a regression one. So instead of predicting a number as we did in a linear regression, for logistic regression, we predict a probability of a particular class, uh, and that the chance that a transaction belongs to a class, or the chance that a class is going to be fraudulent, or the chance that a particular email that has been sent to us is going to be a spam or not. So we use probability in this time. Just know that logistic regression uses probability and it's not predicting a number. So we get to know how it does use the probability to come into a conclusion which class it belongs to later on in this course. So how it works. So the first thing, it calculates a score from the features, just like we did in linear regression. Calculate a particular number. Then we use a particular sigmoid function to squash that score into a probability between 0 and 1. Instead of having like 89% or 0.89 score, we know that since if we have a sigma function and we have a threshold that we have set in our sigma function, let's say if our score is greater than 50%, we want to classify it as high, and if it's less than 50%, it's low. So the sigma function is used to squash the score into a probability between 0 and 1. So if the probability is above 0.5, we predict it's the 0.5 in a normal linear regression problem would be like 50% um, of our accuracy. So but here, instead of using that 0.5, we just want to get a final result of 1 and 0. So it squashes it to a particular probability. So take, for example, if you have 50% accuracy, then it says, or 50% probability, then it says that it's high. But if it's less than that, if it's less than 0.5, which we call 50%, then we'll predict it as low. So remember, there are many important points that we have highlighted here. We talked about sigmoid function. I'm gonna establish that in the course subsequently. Then we talked about logistic regression being predicting a probability, not a number. And we talked about logistic regression is a classification algorithm and not a regression uh, algorithm. So here we're showing you how sigma function is used to squash a number to a probability. So if a score is 5, we can say anytime we see a score that is 5, we can say it's sigma function 0.99 based on what we have set our sigma function to give us. So from that sigma function, we can directly convert it to a probability value. And anything above 50% in a sigma function is usually high class. So if our score is 0, the normal score we'll have gotten in our linear regression. If it ends up to be 0, then we can squash it to 0.5. Then from there, we can convert it to a probability 50%, and that says the class is borderline. That is if we have more than one class. But usually, we usually have binary class, which is 1 and 0. But as well, we can have multi-class problem where we have one or two or more classes to predict. So the last one is you have a negative value in your linear regression. We can squash it to 0.01, which is less than 50%, and that is a low class. So decision boundary, which I call threshold most of the time, is the line or curve that separates the two classes. Logistic regression always draws a straight line boundary, but in a linear regression, while we predict values outside 0 or 1, which makes no sense as probabilities, logistic regression is designed to output value probabilities. So, in a linear regression, we predict numbers as we have established earlier on, but in a logistic regression, we predict probability. We output probability, squashing the linear regression output into a probability value like 50%, 30%, or something like that. Um, I know this is pretty much a math problem, but it's very important we know how the underlying functions that makes classification algorithm works. So this is a typical sigma function. If you look at here, we have the numbers that will be input whenever you have this input, maybe -10 here. So if it comes here, it ends up to be 0. If you look at here, if you have +10, yeah, if you trace it up, you output 1. So in the middle, if you have 0, if you trace it up, you output um 0.5. So this sigma function is something that you set. You can set the value when you are modeling. So because if you move this sigma function to the left or to the right, it's going to change the threshold. Take, for example, if you move this blue line to the front here. So at this 2.5, if this blue line crosses this line here, it will give us 0.5. So at any time you have 2.5 as the value of your linear regression model, then by the time you want to squash it to a logistic regression, it's going to be anytime you have 2.5, it's going to get you a borderline. So this is pretty much the powerful function that changes the numeric values into uh, probability values between 0 and 1. And this is the equation that is used to change the output number x into probability values between 0 and 1. I'm not expecting you to remember this, but this is something you may have to have an insight in, uh, provided you're talking about it outside or you heard it as sigma function. So definitely by this time you have heard it before and it's not going to be too strange. So there's another powerful thing, concept that we ought to know when we're talking about logistic regression or a classification problem. So for a classification problem, we have classification metrics. Usually you will say accuracy might be enough for us to measure to evaluate the classification model, but classification accuracy as a metric is not enough. Um, Accuracy itself is just a percentage of correct predictions. So it sounds simple, but it can be misleading. I imagine a disease affects only 1% of the people, and a model that you just created always predicts no disease. So um, without much mathematical calculation, you can predict that a particular member of an individual in that population will be 99% of the time will have that disease because only 1% will not have the disease rather because only 1% of the people have the disease. So now let's say in the United States you have 1% of the people with HIV/AIDS. So if you just go outside and start predicting that okay, anybody you see, you can actually in 99% of the time you can predict that that person has no HIV disease. So and you will be accurate. So that is what we mean by accuracy as a metric. But that is not enough, especially when your data is not balanced. It's not it's an imbalanced data. So here we say a model that predicts no disease for a particular um, population who do not who only have 1% of the people to be having a disease. We consider that model to be completely useless, despite the fact that it's 99% accurate, because it will never catch a single sick person, or it might not catch a single sick person in many attempts. So, as a result, we need better metrics. So here we have a confusion matrix, which shows up four possible outcomes. We have the true negative outcomes, we have the false positive outcomes, we have the false negative outcomes, and we have the true positive outcomes. The true positive is when a model predicts high, and actually the output is the reality is high. True negative is when a model predicts low, and actually the reality is low. So both true positive and true negative is when the predicted and the actual values are the same. Now, when you say false positive, a false positive is whenever a model predicts a high value, but actually in real life, the value is low. We call it false alarms. And when the last one is false negative, this is when a model predicts low, but actually in the real life, the outcome or the reality is high. That means the model missed it. So here's just a simple picture that you can use to get familiar with uh, confusion matrix, which is the one of the best evaluation metrics for evaluating a classification model. So there are other metrics that we use for classification problem. Uh, Majorly, you're gonna have to use this if you are going to end up being a data scientist. Um, we talked about confusion matrix, which gives us true positive, true negative, false positive, and false negative. So using this confusion matrix, we have other metrics that we use as a standard, and it is called the precision, recall, and F1 score. So precision is it's about quality. You take, for example, you went fishing and you threw your net into the sea, onto the water, and you see 10 fish inside. Nine of them are actually salmon, which of course that's what you wanted. So in this point, we say the precision is 90%, and we say it's very high. So precision is whenever the model says I found it, how often does it actually come out right? Um, so for precision, the goal is always to avoid false alarms. Like for example, in our fish analogy, we say when you catch trash or the wrong fish, that's a false alarm, right? Our target is salmon. So, and out of the 10 fishes we caught, we had nine salmons. So we say we have a very high precision. Now let's go to recall. Recall. Recall talks about how much of the total did you catch. Remember, we're talking about fishes, right? Uh, and we are specific about salmon. So recall, just remember, when precision is about quality, we say recall is about quantity, like how many, how much of the total did you catch? So if there were actually 100 salmon in that lake that day, but your net only caught nine of them, then we say your recall is very low. Yeah. So in a name and definition, we say out of all the things that were actually there to find, how many did the model manage to grab? So the goal is to avoid missing out. So we don't want to leave fish behind in the lake. So we say precision is about quality, recall is about quantity. Then the last one is the balance, which is F1 score. So F1 score is a balance between both quality and quantity, precision and recall, which especially is useful if your groups are uneven. So like when we say a group is uneven, like we say a 1% population of those who have disease in the country, that is uneven. You don't want to use some measure of accuracy or precision recall, but you want to use everyone's score uh, in that scenario in order to evaluate your model. Before you say a model is performing pretty good, especially when you have a unbalanced data or an unevenly sized data population. Uh, the F1 score is like a performance grade that averages the two. So you can't cheat the system by just having a tiny net with one perfect fish. So high precision, low recall, or draining the entire lake to get every fish. High recall, low precision. I know this is pretty much an introduction, so I'm not expecting you to catch this once and for all. Because myself, I never caught it even after 3 or 4 attempts. So just get a hang of this at first, then develop your knowledge on this as you go on. So I give you a table here that gives you a summary of what we talked about, precision recall and F1 score. And there's also a formula that's attached to it. So TP means true positive and FP means false positive. FN means false negative and PR means precision recall. So when does precision matter more? So precision matter more when false alarms are costly. Yeah. E.g., you don't want to flag a customer that is good as being fraudulent. So also when does recall matter more? When missing a positive is costly. When you're missing out a positive um, indicator, if your model is not catching some specific positive value, then and it matters to you, then the recall, you have to use a recall. Recall will help in this scenario. Oh, so e.g., you're missing a disease diagnosis. Here we also have a table that we generated through the code. You can look at the code by clicking on show code, but for now we are not putting our effort in understanding the code this time. We just want to understand the concept. Uh, so here we have precision recall and F1 score. And in the last column, you see a support. So support is just telling us how many data samples of low sales value that we have in that test test data set that we use to generate this table. So anytime you are running these metrics, you typically run it on a test or on evaluation data set just to understand how well your model is performing. So here's a confusion matrix that we have from the table. So here we have eight, eight high value, predicted value is high, but sorry, the predicted value is low, but actually in real life, in the reality, the actual value is high. So here we have predicted value to be high and the actual value is high. Here we have the predicted value to be low and the actual value is low. Here we have the predicted value to be high and the actual value is low. So this is introduction to confusion matrix. And again, reading the confusion matrix, let's look at the heat map above and we will understand on the top left corner, as I said earlier on, the transactions correctly predicted as low sales. So the model correctly predicted 89 transactions as losses, which of course in reality they were losses. And for the top right corner, the same thing for false positive, which is the transaction predicted high, but actually low, which we call false alarm. The bottom left corner shows the predictions are low, but actually they are high, which is a missed positive prediction. We missed that high value, right? The model, not we. The model missed it. So the bottom right, true positive transactions correctly predicted as high sales. These they are high sales, and the model were able to predict as high sales, and it's about 91 instances. So a good model has large number on the diagonal top left and bottom right, as we see here. So a good model will always have large number on the bottom right and top left. Um, just to show that some transactions that were predicted low were actually low. Many transactions that were predicted high were actually high. So here at the corner here, both of them must be high for a good model. Just remember that. Yeah, so I have a little practice challenge for you all. So you have the cell below. You can run the classifier, but there's a different target. We have a high price, which is in price per kg. We already developed the code. Just run and observe. You don't need to put a new code there. Just run the code, observe it, and put your answer uh, at the bottom of the code here. So next, we're gonna go over unsupervised learning in the next tutorial rather, in this module 5. We're gonna go over unsupervised learning. So before then, I urge you to go over the challenge, go over the code. You don't have to write new code. Get familiar with how the code are being written, and we'll see you next time. Until then, keep coding.